extrinsic semiconductors. Welcome to Decreations Resources. We have spoken about intrinsic semiconductors. Now let's talk about extrinsic semiconductors. So far we know that due to thermal excitation, electrons and holes will be created, but their number is going to be fixed for a given semiconductor at a given temperature. Now, it may be required to vary the conductivity of the semiconductor. So how do we do that? Now, this conductivity variation is possible by doping. So what is doping? Doping is the process of addition of impurities in the semiconductor lattice. And the semiconductor is then going to be called extrinsic semiconductor. Of course, we can't add any random impurity. They have to be selected in such a way that it either increases the electron concentration or hole concentration. So there are going to be two types of doped semiconductors. There will be N-type semiconductor in which the number of electrons is significantly larger than the hole. And there will be P-type semiconductor in which the hole concentration is significantly larger than the electrons. Now in N-type semiconductor, electrons are in majority and they will be called the majority carriers while holes will be minority carriers. When it comes to P-type semiconductors, holes will be majority carriers and electrons will be minority carriers. Now, what exactly happens when you add impurity? When impurities are added to a semiconductor, additional energy levels are created. If this energy level is lying within the band gap of a semiconductor, additional electrons and holes can be created. Let's take example of impurity like barium, aluminum, gallium, indium, basically the column 3 from periodic table. If such an impurity, that is a trivalent impurity, is added to silicon, additional energy level called acceptor level, at energy level you can call it as EA. So this acceptor level is going to be created near valence band. Now since there are only 3 electrons in external shell of these impurities and there are 4 neighboring silicon atoms which require 4 electrons for covalent bonding, that means there is lack of 1 electron and it can accept 1 electron to complete the covalent bond. So in that sense, these group 3 impurities will be called acceptor impurities. Now since acceptor energy level is very close to valence band edge, which we can call as EV, V corresponding to valence band, you require very little thermal energy to excite the electron from valence band to the acceptor level. Now at room temperature, all acceptor levels get filled with electrons. So this results in creation of the holes in valence band. For example, if you dope 10 raised to 15 atoms per centimeter cube of aluminum in silicon, it will result in the same number of holes in the valence band. So a large number of holes can be created by doping to make it P-type. So by controlling the number of dopants, you are precisely controlling the conductivity. And in this case, this will be called a P-type semiconductor. Now what about the N-type semiconductor? The situation is similar. We want to increase the concentration of electrons in conduction band, and for that matter donor type of impurities will be added. So elements like phosphorus, arsenic, etc., which belong to the fifth column in the periodic table, can be added to silicon, and that will result in a donor energy level, you can call it ED, which is very close to conduction band edge, which is called as EC. So these impurities, which have 5 electrons in their external shell because they are pentavalent elements, now have only 4 neighboring silicon atoms. So the requirement was only for 4 electrons. And now here there is an extra electron which can be donated. So column 5 impurities are called donor impurities. Now again, since the donor energy level is very close to the conduction band edge, it will require very little thermal energy to excite all the electrons from the donor level to the conduction band edge. So at room temperature, practically all electrons at donor energy level get excited to the conduction band. So in this manner, a large number of electrons can be created in the conduction band, and so this is called as N-type semiconductor. So we have understood that if you add a trivalent acceptor impurity to silicon, it will generate a P-type semiconductor. So for example, if you add aluminum to silicon, it will generate a P-type semiconductor. But if you add pentavalent impurity like phosphorus to silicon, it will generate a N-type semiconductor.